Hello everyone, welcome back. In this video we'll be taking a bit of a look at theorems in ordered fields. This video is the second part of the what we did continuation of what we did last time. So we're told that x is greater than y and that z is greater than 0, and we're told to prove that xz is also greater than yz. So visually this looks something like this: 2.1 is greater than 2 is greater than 1, and we're told, for example, 2 or 3 is greater than 0. So 2.3 is also greater than 1.3, which is 6 is greater than 3. So we know this is true. Let's take a look at how we can prove this. So remember from the previous video, we can write x is greater than y as x minus y being in P. Since x is greater than y, x minus y will also be positive, since both x and y are positive. So x minus y is also in P. And since z is greater than 0, z is also in P. So we need to show, so we know this part, we can assume this part. So we need to show that xz is greater than yz, which can be written as xz minus yz being in P. So x minus y, since x minus y is in P, by OM, I hope you guys still remember that by OM, if two elements x and y are in P, if two elements x is in P and y is in P, then x dot y is also in P. That's what OM says, that's what order of multiplication says. So since x minus y is in P and z is in P, x minus y dot z is also in P. So by distributivity, which was the ninth field axiom, this can be written as xz minus yz also being in P, and this is what we needed to show. The proof is done. Let's take a look at another one. So we have to show that if x is greater than y, and if both x and y are greater than, this has to be a 0, are both greater than 0, but z is less than 0, then xz is less than yz. So this is pretty much like the opposite case to the previous one. So x greater than y can also be written as x minus y being in P. And z, since z is less than 0, z is a negative number. So the negative of a negative number, that is negative z, will be in P. So for example, if z is negative 2, since z is less than 0, then negative z will be negative 2, which is positive, which will be in P. So negative z is in P, and we need to show, we can assume this, we know this, we've been told this, we need to show that xz is less than yz, which can be written as yz minus xz being in P. So we'll use OM again. So we'll multiply, since x minus y is in P and minus z is in P, we'll multiply both of them together, and we'll still get an element that is in P. But that's what OM guarantees us to be. So multiplying these two together, we get minus xz plus yz being in P. We get this by distributivity, which we can rearrange it by, since addition is commutative, sorry about that, minus xz is also in P. And this is exactly looks like what we need to show. So we're done with the proof. Let's take a look at another one, a bit more complicated one. So we're told if a is greater than 0, then a inverse should also be greater than 0. For example, 2 is greater than 0, then 2 inverse, which is equal to half, is also greater than 0. So let's take a look at how we can prove this. So we are told a is greater than 0, so we can assume a is greater than 0, i.e. a, that is a is in P. So we need to show that A inverse is in P, or A inverse is greater than 0. So the three cases, let's do a proof by a proof by cases this time. So the three cases, the OT says that A inverse is either greater than 0, that's the first case, or A inverse is less than 0. In this case, it will be in P, this will be in negative P, or A inverse E is equal to 0. So if we can eliminate two cases, we'll get the first case and we're done. So let's try eliminate case 2 and case 3. If we can make sure that case 2 and case 3 are not possible, then case 1 is automatically possible, because OT tells us that one of the cases has to be true. So let's see if case 2 and case 3 are not possible. In that case 1, we don't even need to prove case 1. Case 1 will automatically be true. I'm sorry, case 2 is negative A inverse. So case 2. So if negative, or if A inverse is less than 0, then negative A inverse is greater than 0. Since case 2 says that A inverse is less than 0, if A inverse is less than 0, then the negative A inverse will be greater than 0. For example, if negative 2 is less than 0, negative of negative 2 is greater than 0. That's how we get this. So that's how we get this statement. So let's take a look at how we can do this. So I'm going to multiply both sides by A. Since negative A inverse is greater than 0, that means negative A inverse is in P and A is in P. We're told that we can assume that. So if we multiply both sides, if we multiply a negative A inverse by A, we'll get an element that is still in P. So this is a valid step. So I'm going to multiply negative A inverse with A. Let's see what happens when we do that. Right, we get this, which can also be written as negative A inverse A. So we know that from the multiplicative inverse, since A inverse is the inverse of A, we get negative 1, and we know that 0 dot A is of course 0. We get that negative 1 is greater than 0, and this is absolutely strange. We negative in the number line, negative 1 is behind 0. So this statement that negative 1 is greater than 0 is a strange statement. This is a contradiction. So this um, we now know, because of this contradiction, we now know that case 2 is absolutely wrong, because negative 1 can never be greater than 0. So let's see if case 3 is also wrong. If we can show that case 3 is also wrong, we're done. If case 2 is wrong and case 3 is wrong, then case 1 is of course has to be right by OT. So case 3 says that A inverse is equal to 0. So I'm going to follow the same template and try to see what happens if we multiply both sides by A. So by multiplicative inverse, we still get 1, and A dot 0 is of course 0. So this is another contradiction. This is another strange thing which is happening. How can 1 be equal to 0? Only 0 is equal to 0 and only 1 is equal to 1. So this is a strange thing which is happening. So case 2 is wrong, case 3 is wrong, which only leaves case 1 to be right by OT. So A inverse is indeed greater than 0. If A is greater than 0, then A inverse is greater than 0. We are done with the proof. So this is a proof by cases. I hope you guys learned how to do proof by cases from this example. So let's take a look at the final example for the video. We are told that if A is greater than B and B is greater than 0, we're told to prove that A inverse is greater than is less than B inverse. So for example, if 3 is greater than 2, then where to for example, then 1 over 2, so I'm sorry, 1 over 3 is less than 1 over 2, which is right because 1 over 3 is 0.33 and 1 over 2 is 0.5. So we know this is right. Let's see how we can prove this. So we know we can assume A is greater than B, i.e. that is the same as A minus B is in P, and B is greater than 0, which is the same as B being positive. Remember that if B is greater than 0, that's the same as saying A is greater than 0, because A is greater than B, which is greater than 0. So A is also greater than 0. So A is greater than 0 means A is also in P. So if B is greater than 0 and A is greater than 0, and A is greater than 0, then in the previous part we proved that if A is greater than 0, A inverse will also be greater than 0, so as B inverse, which will also be greater than 0. So B inverse, so A inverse is also in P, and B inverse is also in P. So let's see what we can uh, how we can manipulate what we know to show what we want. So we need to show that B inverse minus A inverse is in P. So let's see how we can do that. So we know A minus B is in P, and we know that A inverse is in P and B inverse is in P. So let's use OM. Since they're all in P, when we multiply all of them together, the element we'll end up with will also be in P. That's what OM guarantees us. So let's see what happens when we do that. Remember, when you're doing proofs of theorems in fields and ordered fields, you're just trying to manipulate what we know to try and get what we want to show. So we want to show this and we know this, so we have to try and manipulate this to get something that looks like this. So multiplying all this together by OM will guarantee us that it will still be in P, since all of them together are in P. So this is the same as A inverse B inverse by distributivity, which is our ninth field axiom. And I'm going to use distributivity again to get A dot A inverse B inverse minus B A inverse B inverse, which will also be in B. I'm using distributivity, and this will boil down to 1 dot B inverse. And if you use if you use the fact that multiplication is commutative in fields, we can exchange the places of B and A inverse, and we get that B times B inverse is also 1. So we get 1 dot A inverse also being B, and 1 dot B inverse is B by the fact that 1 is a multiplicative identity, and Mn by multiplicative neutral, we get that B minus A inverse is also in P, and this looks exactly like what we needed to show, and therefore we're done with the proof. So I hope you see that proofs in fields and ordered fields is just simply manipulating what we know so that we end up with something that looks like what we want to show. So I hope you guys